He got the graduate and PhD degree at Flinders University in Adelaide, South Australia. Then he got a postdoc position at Manchester University with Professor Frank Reed, and then another postdoc position at GILA, a joint research center of the University of Colorado and NIST with Arthur Phelps. Then he returned to Australia, to the Australian National University in 1983 with Bob Crompton, working mainly in the plasma physics area. And then he was the head of the Atomic Physics Laboratory at the Australian National University around the 90s. After that, he was the director of the Center of Antimatter Interaction, which is probably one of the most important centers devoted to research in matter, antimatter, positron, antiproton, and so on. So his contribution there at that moment was huge, around the 90s. Then he was the director of the Research School of Physics at the ANU until 2015. We can say that his numerous contributions to this field make a reference, is always a reference for the community of electron, positron, and cold atoms. So today, Steve Buckman is talking about low-energy electron and positron interaction, cross-section, reaction dynamics, bound state, and resonances, and some application. So, Steve, would you like?
Well, thank you, Gustavo. It's a really great pleasure to be here in Toledo, this absolutely gorgeous city in the middle of Spain. And I'd like to thank Gustavo for those kind words. It's a special honor for me for you to be able to introduce me today. I'd also like to thank the local committee for an absolutely wonderful conference so far. I think for every local committee, the big hurdle is the conference dinner. And last night's, I've been to 15 Icpeacs, this is my 15th, and last night's conference dinner was absolutely fantastic, so well done. And also to thank the program committee for the invitation to speak here today. I'll apologise beforehand, I've got a bit of a croaky voice. I think from too much laughing at the at the conference dinner last night. So I'm located in Canberra, myself and my group. For those of you who don't know much about Australian geography, Canberra is the capital city of Australia. Many people seem to think that Sydney or Melbourne is, but it's actually Canberra, and that's where the seat of our federal government is. And as Gustavo said, I'm going to talk about low-energy electron and positron interactions today, mainly focusing on experimental advances, and it'll be a very personal sort of a tour through work that we've been doing at ANU and with collaborators around the world, and trying where I can to tie in with theory, because in this area it's particularly useful for us to be able to do that. And I should acknowledge the support and funding of the Australian Research Council. We had a Centre of Excellence for 8 years to develop positron physics in Australia, and it was something that was a unique experience for us, and much of the work that I'll talk about later in the talk today has come out of that funding. So we've had good support from the Australian Research Council. This is a picture of Canberra. This is taken in summer. When I left a couple of weeks ago, there was actually some snow out here on the hills. We've had a very cold winter, and snow is somewhat unusual this time of the year in Australia, but Canberra's up at 750 metres above sea level, so we occasionally get a bit of snow. And the ANU campus is here, and our research school of physics is located down here by the lake, and over here on top of the hill is where the federal government is located. So we're about 2 kilometres from our funding agency. Sometimes that's an advantage and sometimes it's a disadvantage. That's another picture of the federal parliament. Canberra is a city of wide avenues and lots of open space. It's a sort of designer city. It's just had its 100th, we've just had our 100th birthday, which in Australia is quite old. And these are some of the locals. I think they've just heard that the next Icpeac is going to be in Australia, so they're very excited. I really should start by acknowledging a whole host of people that have contributed to the work that I'll be talking about today. I'm not going to read all the names out, and those that are highlighted in red are people who are here in the audience today. So there's a significant number of our collaborators from the ANU who have joined us here at Icpeac, and so a large number of staff and students that I've worked with at ANU over the past 20 years or so, and a significant number of people internationally that have contributed and with whom we have contributed research activities. I'm going to commence today trying to outline a little bit about what we do and why, where we are experimentally and theoretically, what the sort of things that we could measure, at least my perspective. And I'll give a very personal perspective about what I think are some highlights of electron collision measurements over probably the last 20 years or so. These three topics here. And then, with enough time at the end, move on to look at positron interactions. I might not be able to cover all of these things, but we'll see how we go. So I don't really have to provide too much of a rationale for collision studies to this audience. I think electron and to some extent later in the piece, positron scattering has been a major part of the activities that have been centered around Icpeac. So it's a core area, or has been a core area of this conference for many years. It's a fundamental scattering discipline. In fact, it provided some of the very earliest tests of quantum mechanics, in particular the minima in rare gas and other scattering cross-sections that were discovered independently by Ramsauer and Townsend, Ramsauer in scattering experiments and Townsend in discharge-based experiments. Those minima couldn't be explained by classical physics where the expectation was that as you went to lower energies, the cross-section would monotonically increase. But these deep minima that were measured in the 1920s, and actually the data still stands up to the test of time, really was one of the first experimental tests for quantum mechanics. And it can only be explained by invoking quantum mechanics. Electrons are a really essential spectroscopic tool, in particular if you want to look at excitation which involves spin exchange, so singlet to triplet transitions from ground state singlet atoms, or vice versa if you have a ground state atom or molecule. And really, these experimental activities have been a key to the development of quantum scattering theory. And part of what I'll talk about today is some of those key developments in the last 20 years or so. Electron, atomic and molecular science is both a fundamental science and really an enabling science, because it underpins many technological and environmental activities, and there's just a few that I've listed here. We've had many talks during the course of the conference this week that have also focused on applications of electron physics in areas such as plasma, gas discharge. This is a medical plasma, and of course in environmental remediation, where discharge physics is a very important activity. And for all of these things, we really need accurate data at the fundamental level, and that's where the scattering information can feed into applications. Positrons, they're the electron antiparticle. They were predicted in 1928 by Paul Dirac, discovered or found experimentally very soon after that by Anderson at Caltech in 1932. And some of the key interest that we have in antimatter interactions with matter is the difference, for instance, with positrons, the different way in which that interaction potential or the interaction takes place. Of course, the most notable is that the Coulomb potential is repulsive for positrons, so they don't penetrate into the charge cloud of the atom or molecule very far, as much as electrons are. Polarization effects, the distortion of the charge cloud during the scattering, is essentially the same for both. A big difference is the lack of the exchange interaction. Of course, with electrons in a scattering experiment, the projectile electron can exchange with one of the atomic or molecular electrons, and that can drive many interesting processes, but it's absent for positrons. Spin-orbit interaction, because of this lack of of penetration of the electron charge cloud in the target, the spin-orbit interaction in positrons is very weak, but it's a significant effect in electron scattering. Big difference, of course, is positronium formation, the formation of this electron-positron bound state that can happen when a projectile positron picks up an electron and forms positronium. Of course, not evident, not there for positron interaction. And then big questions particularly in positron scattering. We know that for electrons there is an abundance of bound states and resonances in just about every target you want to look at. But so far for positrons they've only been found experimentally resonances and bound states in molecular systems. And there's been a lot of theoretical work, and I'll touch on that a little later. There's a lot of applications that are emerging for positrons. I won't talk about this one today, but they've been now used commonly, a technique called positron annihilation lifetime spectroscopy, where they are used as a probe of open space in materials. And the one that I will say a little bit about today is applications of positrons in biomedical science. So they're used as an imaging tool and increasingly as a therapeutic tool in PET scans. And of course, they're also, antimatter's also been the subject of much myth. And if you want to buy a tin of antimatter, you can get it from this company called the Brooklyn Superhero Supply Company. Of course, we buy this stuff, and if you buy it, it comes in a nice tin. You put it in the fridge, and you get cold positrons. You put it in the freezer, and you get ultra-cold positrons. So. And it's green as well, so that's... The finding of the positron was a really interesting story, and if you've got a bit of time, I'd suggest that you read this article from Anderson and colleagues from Caltech. This was published in 1933. The really interesting thing was it was received on February the 28th and published on March the 15th, so it took 15 days between, and that was back before electronic communication. I don't think we can get stuff published in 15 days. There's a really interesting little paragraph in the introduction of Anderson's paper where he talks about the interpretation of tracks that they found. And the one that really appealed to me is that, so they say here that these tracks were only interpretable on the basis of the existence, in this case, of a particle carrying a positive charge, but having a mass of the same order of magnitude as that normally possessed by a free negative electron. This is a great paragraph. Later study of the photograph by a whole group of men of the Norman Bridge Laboratory only tended to strengthen this view. So that was how you sort of went to publication back in 1933. The other really fascinating thing about this paper is that there's no mention of Dirac. There's no mention of Dirac in the text, and there's no reference to Dirac in the paper at all. It's a really interesting and intriguing story, and if there's a lot of background to this, some of it actually was touched on by Gleb Grabarkin in his talk late last week. So I'd encourage you to have a look at that if you have some time. Okay, so for electrons and positrons, very quickly, what can we measure and how well can we do it? So the things that we can measure accurately, and by accurate I mean sort of up to 25 or 30% uncertainty, are these scattering events: total elastic scattering, vibrational excitation, ionization, and positronium formation in the case of positrons. Things that are not so easy to measure include rotational excitation, electronic excitation. These are really limited mainly by the characteristics of the spectrometers that we use, by energy resolution, etc. In the case of electronic excitation, by efficiency, understanding the efficiency of your spectrometer. But dissociative attachment, excited state collisions, and collisions with radicals, and I'll say a little bit more about these two later in the talk. Almost impossible is to measure neutral dissociation, to actually be able to tag neutral fragments after a dissociation process, measure their energies, and put assign a cross-section. So we need to touch base with theory, and so most of the processes can be calculated, but the question really is how well. And for atomic systems, I think theory is in really good shape, and I'll show you a perfect example of that. Also for small molecules, there are a number of highly reliable calculation techniques now, including R matrix and various variational techniques, and some phenomenological approaches, independent atom model approaches, which have proved to be really very helpful in describing cross-sections across the board and at increasingly low energies. But the key point, I think, is that experiment can, in terms of applications, we can only measure about 10% of what we need for these applications. And so we really have to make that link to theory and do this through benchmarking theory and experiment. So in many of the applications, theory needs to be the major provider. And this accurate data and comparisons between experiment and theory are really critical for the field. And a little bit about some of the theoretical approaches, those that are used in both electron and positron scattering in the solution of the time-independent Schrodinger equation. So close coupling techniques have really come into their own over the last 20 years. For higher energies, perturbation techniques can be used. There are some special difficulties in calculating molecules, including how one treats the nuclear motion, vibrational excitation, molecular structure, and in particular those systems that may be polar and have long-range interactions through the dipole potential. And of course, the special problem with positrons is the formation of positronium. And describing positronium in the final state of a calculation is an extremely difficult problem. It basically means that the problem becomes a two-center expansion in the final state and poses many difficulties. So, as I said, this is a highly sort of personal walk through some of the things that we've been and others have been involved in over the last 20 years. And so for electrons, I'd like to focus on some results from these areas, and starting off with precision cross-section measurements and comparison with theory. I'm an experimentalist, so I really love to talk about apparatus. I apologize for those in the audience that are not apparatus junkies, like all of us experimentalists, but this is, in some sense, the first half at least, is a typical electron spectrometer. Electron gun here, which provides a source of low-energy electrons, then a dispersive, electrostatic dispersive device where we disperse, so we put the electrons into this device maybe at an energy of 2 eV, disperse them across electrostatically across the image plane, and select a little portion of that, maybe throwing away 99% of the electrons in the process, but having, as a result, a higher resolution beam. We then have another series of optics here which focus into the target region where it crosses with an atomic beam. This apparatus is a little different in that, in this case, instead of having a similar electrostatic analyzer, we have a time-of-flight device and coupled to a position-sensitive detector. So this is a pulsed experiment. We measure all the electrons that depart from the scattering volume. We measure their time of arrival and thus their energy after the pulse, and we measure them over an angular range of about 20 degrees. And this is all enclosed in a vacuum system. It's all UHV compatible materials. So with this apparatus, a few years ago we did experiments on excitation of the n equals 2 states of helium. So the 4 n equals 2 states of helium are here, and I'll show you some results at energies. One energy is just above the lowest excited state, the 2SSS, and another which is above all 4 excited state thresholds. And so for this particular energy here, these are comparisons between experimental results taken with this time-of-flight spectrometer and the very best theories that are going around at the moment. So there's the convergent close coupling calculation from Igor Bray's group, and 2 varieties of the R matrix calculation from Klaus Bartschat and Oleg Zatsarini. And so what's plotted here is the ratio of the 2SSS to the elastic scattering cross-section. And we see some very sensitive differences between the theory, but overall, the agreement between experiment and theory is not too bad. And this is only less than half a volt above the threshold. So that's a really difficult area typically for electron spectrometers to operate, and that's where the time-of-flight technique actually proved an advantage to us. To illustrate just how tricky this is from in this particular regime because of resonances and other scattering effects that are taking place, this is the experiment again, and it's compared to the R matrix calculation for 3 varieties that are separated by only 50 millivolts. And you can see that the difference between these 2 curves, for instance, is 100 millivolts in incident energy. So it's a very sensitive region, and one needs to know both the energy of the particles, the energy of the scattered particles, so that you can make a realistic comparison with the experiment. A little higher energy, so back here we're at 22 electron volts, we're above all of these 4 excited states. We see, I think, exceptionally good agreement between, this is a little bit noisy because the 2 singlet P cross-section starts off very slowly. It's very small at threshold. But in the other cases, we see essentially perfect agreement between experiment and theory for this benchmark system. The interesting thing is that there are some differences that emerge here at the higher and lower angles between the theories, and at present we can't probe those, but that's an area where there's still some uncertainty perhaps. But overall, the agreement here between experiment and state-of-the-art theory is exceptionally good. The next subject I'd like to focus on is an experiment that I was involved in 32 years ago at the University of Manchester when I worked in Frank Reed's group. And we did a series of measurements on the metastable atom excitation function for the rare gases, so for all rare gases. And this is an example in argon. I don't really want to spend too much time on the experiment, but I want to show in a minute where theory has come over the last 32 years. But one of the interesting things in this experimental result is that there are pairs of resonances that are seen in this excitation spectrum. And all of those pairs, there are about 10 of them in argon, have a spacing of 177 millielectron volts, which is exactly the spacing of the iron core, the spin-orbit split iron core in the argon atom. And what it's telling us is that these are doubly excited states, so the electron is attaching to the atom. And what it's telling us is that there's 2 electrons in these doubly excited states that are highly correlated in their motion. And they're sitting a long way away from the core and only weakly interacting with that core. So their position exactly mimics the energy separation of the core. So the really interesting thing in the last few years has been advances in the R matrix calculation, this so-called B-spline R matrix calculation from Klaus Barchat. And this is a comparison between the earlier data, which are kind of the brown points here from Manchester, and a series of calculations which have converged on the experiment. And this is a really outstanding result. For a complicated system such as neon and argon, we see essentially perfect agreement with these calculations with experiment. There's a little bit of scaling that takes place here for the cross-sections, but in the Manchester experiments, the cross-sections were not the focus. It was really these resonance states. So not only do we see perfect agreement, or close to a good agreement in absolute value, but in terms of the structure of these negative ion states, we see essentially perfect agreement. It's a little bit worse and this is sort of a series of techniques that Barchat applied to this over the years until finally, it was probably a 10 or 15 year process until finally converging on these results. Not as good in the heavier systems as krypton and xenon, but essentially perfect for neon and argon. So I want to move on now to talk about measurements on radical species. And this is an experiment, well, let me just perhaps provide a little bit of information. So the rationale behind this is that radicals are readily produced in gas discharge environments, any sort of gas discharge or plasma environments. And these radicals can have large cross-sections. They can be open shell, highly polar systems, and the interactions between the electrons in a discharge and the radical can have a major impact on the discharge environment. Very difficult to study experimentally. They're very difficult to make, and there's very few studies of these things of absolute cross-sections. So they're very difficult to produce, and in particular to characterize what the makeup of the beam that you produce is, and I'll say something about that in a minute. There's not much theory on this subject either, largely because these radical components are open shell, highly polarizable, highly polar systems. So they present a challenge for, and they're molecules, so they present a challenge for theory as well. This is the apparatus that was used to study these. This is from Michael Brunger's group at Flinders University in South Australia. This is really a tour de force experiment in my view. Michael's group made a radical source, which was a pyrolysis gas nozzle, which was also a supersonic jet, so a nozzle and skimmer, and this was operated at about 1,000 degrees centigrade typically. And so a beam of junk would be produced, hopefully containing some radicals, would pass through an electron spectrometer where they would be crossed with an electron beam, and there were 15 or so detectors arranged around the scattering center so we could detect multiple angles at the one time. The beam was then analysed in this time-of-flight mass spectrometer so we could look at the constituents of the beam and try and extract the cross-sections. And that's a picture of the apparatus. It's a thing that's about 5 meters long and multiple pumping systems. These are some results. This is for CF2, which is produced through pyrolysis of CF4 at about 1,000 degrees centigrade. And these are absolute differential cross-sections. This is angle and cross-section here, compared to a Schwinger variational calculation from Caltech from Vince McCoy and Carl Winstead. I don't have the energy on these. Oh, yes, I do, sorry. 40 eV and 50 eV. There's a whole range of measurements down as low as 5 electron volts. And in general, the agreement between theory and experiment was surprisingly good. There's another variational calculation, the dashed line here from the Brazil group, using the same technique largely, the Schwinger variational technique. Another radical that was produced was CF3, which was produced by pyrolysis of CF3I. And a quick glance at some of the measurements for this. In this case, we have complete disagreement between experiment and theory. At this low energy of 7 electron volts by about a factor of 10, and that still hasn't been uncovered. Interestingly enough, at higher energies, around 40 and 50 eV, theory and experiment come together. So there are some either unknown experimental issues or unknown theoretical issues at the lower energy for this open shell radical molecule. Another bonus out of this experiment was that in the beam we produced atomic iodine. And so we were able to extract, you can see with very large error bars unfortunately, but able to extract the first differential measurements on atomic iodine at these energies, 40 and 50 electron volts. And there's a range of calculations that we compare with here, including the R matrix model. The final topic for electrons I wanted to talk about was measurements on excited species. So low temperature discharge, in much the same way with radicals, can contain excited atoms and molecules. In particular, if they're either long-lived vibrational states or long-lived metastable states, you can generate significant equilibrium populations in these environments. Things like homonuclear diatomic molecules, for instance. One that I'm interested in is metastable atoms and molecules. These things have very long lifetimes. The one that I'll talk about, in fact, has the longest atomic lifetime for an atomic valence state. Large internal energies. In the case of the rare gases, metastable helium has almost 20 electron volts internal energy. They can be excited and ionized with very low energy electrons. They have huge scattering cross sections, as we'll see. And they can be sources of Penning ionization. So a helium metastable can ionize just about anything, any other atom or molecule, with the exception of neon. And as I mentioned, the cross sections for this are really very large, and much larger for Penning ionization, much larger than 100 square angstroms. But experimentally, once again, they're difficult to produce control targets, The densities that one gets, typically you have to use a discharge source for these. The densities are low. There's a lot of background noise, photons, electrons, ions, etc. And they're tough experiments, so there are only really a few in the literature. We decided to do some work on metastable helium. It's a sort of prototypical system. Has a lifetime of around 8,000 seconds if you leave it alone and don't interfere with it. A binding energy of 4.8 electron volts, so and a polarizability more than 150 atomic units. So it's a bit like an alkali in many respects, very reactive system. And to make this, you need to have a discharge-based source. You can only produce it by electron impact. And those sources typically result in low densities and large backgrounds, as I mentioned. So we went to a laser cooling and trapping experiment to try and improve, particularly on this density and particularly on the background. The experiment that we put together was a very complicated piece of apparatus. It consisted of 3 or 4 stages of laser cooling. First of all, a transverse cooling stage here at the exit of a helium, liquid nitrogen-cooled helium discharge. So the idea of this was that as the metastables were spewing out of the discharge, we were using optical pressure to bring significant numbers of them back onto axis and into a parallel beam. We then put them into so out of the helium discharge, they're traveling at about 500 meters per second, liquid nitrogen-cooled helium discharge. We put them into a Zeeman slower, where a counter-propagating laser beam. These lasers are all tuned to the 2-triplet-S to 2-triplet-P transition. A counter-propagating laser beam would interact with the atoms, and each interaction would transfer a small amount of momentum to the atoms so that you could change their velocity by around 1 meter per second for each photon excitation cycle. And ultimately, we can slow them down. We could slow them down enough that we could even turn them around and push them back, but we didn't want to do that. What we did then with a slow beam that emerged at maybe 50 or less meters per second was put it into a 2-dimensional magneto-optical trap where it was focused, and then into a 3-dimensional magneto-optical trap where the atoms were trapped. And in this way, we could increase the density for the experiment from typically around 10 to the 7th per cc at this stage to around 10 to the 9th in the trap. The experiment we did then was a very simple one. We have an electron gun crossing some diagnostics here to measure the characteristics of the trap. Electron gun with a pulse of electrons that we can push across the trap. Essentially, any electron that interacted with a metastable helium atom would kick it out of the trap, irrespective of the type of interaction that took place. So all we really needed to do, and it seemed very simple in principle, was to measure the trap loss rate and then plug that into this equation up here where we could get the total scattering cross-section for electrons off metastable helium. And this was the result. We got some very nice absolute data which compared extremely well, again with these 2 state-of-the-art calculations, the CCC and RMPS. Just to point out, this is a cross-section that surges up at low energies, and at 2 eV, the cross-section for scattering from the metastable state is about a factor of 100 larger than the ground state. And it's still 30 times larger out at 20 electron volts. So these cross-sections are extremely large and extremely important. Oh, as a sort of bonus out of this measurement, we were able to, I won't say too much about this, but it was kind of neat, we were able to measure the lifetime of the 2-triplet-S state. The only previous measurement of that had been about 30 years ago in a plasma environment. So with a little bit of technical know-how, which was largely supplied by this guy, Andrew Truscott, we were able to measure a value for the lifetime of the 2-triplet-S state at 7,870 seconds, plus or minus 500, which, as it turns out, agrees perfectly with the best QED calculation going around, which is now more than 40 years old. So the previous measurement was this one here back in the 70s. So now a move to positrons, some would say a move to the dark side. And what I'd like to try and highlight here are some measurements. Firstly, a technology that is being used increasingly in a number of labs around the world, trap-based magnetised beams. I'd like to say a little bit about work that we've done with such a device for measuring cross-sections, scattering and positronium formation, some interesting threshold effects that we found in some of the cross-sections, and finish up with some insights perhaps into applications of positron interactions into biology and medicine. So I think one of the big boost that this field has received over the past 20 years was the advent of the so-called Serco trap. Cliff Serco and colleagues at UCSD developed a technique for trapping and cooling positrons, which has turned out to be extremely useful for a whole range of measurements. So these traps, typically they use a sodium-22 positron source, and the sodium-22, the energy spectrum from sodium-22 looks something like this. It's over many hundreds of kilovolts, all the way up to almost 1 MeV. So the positrons can be emitted from sodium-22 anywhere in this spectrum. Then firstly moderated using solid neon crystals, and the positrons collide in the scatter in the neon matrix, and they're ejected from the neon matrix with an energy of about 2 electron volts and a width of about 2 electron volts. So we go from hundreds of kilovolts widths down to this band here, which is, say, at an energy of around 2 eV and a width of around 2 eV. In doing so, we lose 99% of the positrons. We then put them into a buffer gas trap. The trap is a series of electrodes about 30 centimeters in length, which contains N2 and CF4 gases. And we allow the positrons to very lightly interact with those two gases and cool. Through doing so, through electronic excitation and vibrational and rotational excitation, they cool to room temperature. So we can extract a beam of positrons with an energy width of around 50 millielectron volts from this device. So we end up with pulsed positron beam. This is intended to indicate the pulsed beam here. We can vary its energy electrostatically, of course, but this technology allows us to greatly reduce the energy width of the beam and have a much more controlled source of tunable positrons. The overall efficiency is about 0.1%. So with a 50 millicurie sodium source, which is a very strong source, we end up with about a million positrons per second in our pulse beam. And then we can pass that into a gas cell and do energy analysis and scattering. This is a schematic of the apparatus we have at the ANU. So our sodium 22 source and neon moderator is in here. The neon is frozen onto the sodium 22 source at 6 degrees Kelvin. So it's a neon crystal that sits on the source. The positrons are then transported electrostatically and magnetically confined into the trap. From the trap, the pulse beam passes into a gas cell where we have the gas, or it could be a biological molecule of interest. And then we can energy analyze what passes through after interactions with a retarding potential analyzer and detect the positrons with a multi-channel plate. Before saying anything about some of the results, I'd just like to touch on this special beast positronium. So positronium is a hydrogen-like bound state of an electron positron formed in a scattering interaction with an atom or molecule, and the positron strips off an electron, leaves the atom or molecule ionized. And positronium can come in two varieties, either the singlet, where the spins are anti-parallel, which is known as parapositronium. It has a very short lifetime of around 120 picoseconds. One that's used more often and is of more interest to us is orthopositronium, the triplet variety, which decays by 3 photons, and its lifetime is 142 nanoseconds. So it hangs around, and you can use it. You can make beams of it, as we've heard in talks earlier in this meeting. Interesting thing with positronium is it has a binding energy of half that of atomic hydrogen because of the reduced mass. So you can form positronium 6.8 eV below the ionization potential for whatever the atom or molecule is. So in the case of helium, the threshold for positronium formation is 17.8 eV. That therefore is also the threshold for ionization of one ionization channel of the helium atom with a positron. And for sodium, an atom like sodium, which has a low ionization potential, positronium formation is open at 0 electron volts. So with a very low energy positron, you can both ionize sodium and form positronium. So it's a sort of soft ionization technique. And we have an interest because for these large biomolecules, the positronium formation threshold is typically a few electron volts. So, some cross-sections, both scattering and positronium formation. This is kind of an overview of what these cross-sections look like. These are absolute cross-sections, total cross-sections for the helium atom. So the red curve here is the grand total cross-section. So that's the measurement of any and all scattering possibilities. Down here at low energies, there's a Ramsau-Townsend minimum, just around 1 electron volt. The other key feature here is at 17.8 electron volts, where the positronium formation threshold is, and then the cross-section really kicks off as a result of both positronium formation and inelastic scattering. The blue curve here is the positronium formation cross-section. So, and it's a typical shape. It has its maximum around 10 or 15 electron volts above its threshold. At that maximum, it's typically around 50% of the total scattering probability for the atom. The green curve here is all other inelastic events, bar positronium. So this is electronic excitation and ionization. And down here are the excitation cross-sections for the 2 singlet S and the 2 singlet P. You note that there's only 2 here. There are 4, as we saw earlier, there are 4 excited states in the n=2 manifold of helium. But the triplets, the 2 triplet S and the 2 triplet P, can only be accessed by electrons. So with positrons, you can't excite these states. And we only see 2 states, and their cross-sections are very small. If we take a little bit of a closer look at this area, the Ramsau-Townsend minimum, and compare with 3 recent theories, or actually one of them's not so recent, but 3 of the best theories going around, which is the close coupling calculation, a many-body theory calculation, and a variational calculation. And we see essentially perfect agreement between experiment and theory for this cross-section. We can look at inelastic scattering, those 2 curves that I showed you a little earlier here in some more detail. And again, the red points, there were some earlier measurements using a time-of-flight technique by Paul Coleman. These are our recent measurements from the ANU, and compared here with a CCC theory, which was the first case where they managed to put in the multi-centered nature of positronium formation into the calculation. And again, we see really excellent agreement between experiment and theory. This is what the positronium formation cross-sections look like. This is in the neon atom. The data, there's reasonably good agreement here between 3 experimental groups. Ours at ANU are in the red. The dense blue points here are from University College, and the little open circles are from Cliff Serko's group in San Diego. And a number of calculations, coupled channel calculations and distorted wave calculations. And that's sort of typical of the level of agreement with positronium formations. Positronium formation cross-sections is another example for the argon atom, where there's a little bit more scatter between the experiments and a bit better agreement with theory. Threshold effects. I need to go back again to the 70s as the introduction to this, and this was an experiment that was done in Germany on elastic electron scattering from the sodium atom in the region of the first excitation potential in sodium, which is the sodium D-line transition at 2.1 electron volts. And what they saw was these amazing features that occurred in the elastic channel. So this is the elastic scattering cross-section as a function of energy as it passes through the onset of the sodium D-lines. And these structures were seen 30 or 40 years prior to this in nuclear physics by Wigner, and were given the name Wigner cusps. So these are Wigner cusps that occur in electron scattering. Also from the Manchester group in the mid-70s, they saw similar cusp-like behaviour in the elastic scattering channel at the onset of the 2 triplet S and 2 singlet S levels in helium. And we were interested, we didn't think much about this until we actually saw it in the experiment. We saw some broad features in the elastic scattering cross-section for positrons interacting with rare gas atoms. And we believe that the process that we're looking at is exactly the same as that in the sodium D line. So if you look at the rare gases, positron elastic scattering from helium, neon, argon, krypton, and xenon. So this is the elastic cross-section with the blue line through it in each case. The other points here are the positronium formation cross-section, this being the positronium formation threshold, this being the first inelastic scattering, first excited threshold for each of the atoms. And we see these interesting cusp features. In the case of xenon, it's about a 10% effect in the total elastic cross-section. And so these are, in the same way as with the sodium case, we have a very strong cross-section turning on here in positronium. And these two states, the positronium formation channel and the elastic scattering channel, are strongly coupled. And positronium is robbing flux ultimately out of the elastic channel. And the rise below threshold here is interpreted as potentially as virtual positronium formation. So it's a really interesting process. We had a look, so this is the case of neon. We had a look in some molecules which are isoelectronic to neon, so containing 10 electrons. So methane, ammonia, and water. And we don't see any evidence of a cusp in those molecules. And the argument here is that in all of these molecules there are so many. So in the case of the atoms, the only 2 channels that are open here are elastic scattering and positronium formation. But in the case of the molecules, there are many other channels that are open for vibrational and rotational excitation. So the channel coupling is being spread over all of those states, and we don't see the effect of the cusp in the elastic scattering channel. Resonances and bound states. This has been an area of great excitement and activity in positron interactions over the last 10 years or so. There's now clear experimental evidence for molecular resonances and bound states in annihilation measurements that were done at the University of California in San Diego by Cliff Serko's group. They've seen these vibrational Feshbach resonances very close to zero energy. And these resonances, the little bars here, are actually the vibrational levels. These are all alkane molecules, and these are the vibrational levels for the neutral molecule. And there's a small shift between these peaks and the vibrational energy levels, and that shift is interpreted as the binding energy of the positron to the molecule, and these resonances here are a manifestation of vibrational excitation of that bound state. And the binding energies that they've measured have been as large as 300 milli-electron volts. And there's a great review, if you're interested in this subject, written by Serko and collaborators and Gleb Grubakin a few years ago. In the case of atoms, it's not quite so clear. There's a plethora of calculations now from the late Jim Mitroy and Michael Bromley and co-workers. And in fact, many years ago, they introduced this so-called positronic periodic table where variational calculations that showed that these atoms that are highlighted here in red would bind a positron with a variety of binding energies. In recent times, and in fact there was a poster today from Victor Flambaum's group, they've identified a whole host of other candidates, including excited states of atomic systems that are candidates for binding. And the models that Mitroy and Bromley had were the binding for these atomic systems. They could largely break up into two visualize in 2 models. One where the positron polarizes the charge cloud of the atom and is attached in some long-range polarization potential. And another where there's a virtual positronium formed, and that is aligned and attached to the residual ion core. So there's a wealth of calculations now for all of these states, but so far, not a lot of experimental evidence. One that we investigated a few years ago was a calculation that Jim Mitroy and Michael Bromley did on the 2s squared doubly excited state of the helium atom. So this is the upper reaches of the helium spectrum converging on the double escape threshold. This is actually an energy of around 57 electron volts. And through these variational calculations, they found that the 2s squared singlet S doubly excited state supported a bound state and also a shape resonance just above that. So this was very exciting, and we tooled up to do an experiment on this. And we did some measurements around these energies. So the vertical lines here are the predicted, theoretically predicted energies. These are measurements of the total positronium cross-section and the total scattering cross-section on the top and the positronium formation cross-section on the bottom. And unfortunately, we haven't seen any. This was an experiment that we cranked for many weeks, and we haven't seen any evidence, any strong evidence of these bound states. What we believe that these energies are well known. What we don't know is what the lifetime or the cross-section for these resonances are. And we can put a sort of upper limit on that from these measurements, but so far, no cigar. There is some hope, though. This was an older calculation from Jim's group for positron magnesium scattering. This is a total scattering cross-section. This is a calculation which has also been repeated and verified using the CCC method. And this cross-section has a resonance with a maximum above 1,300 square angstroms. It's bigger than anything I've ever seen in electron scattering, and I think opens up some really interesting possibilities for the future. And that's something that we'll be tooling up to have a look at in the not too distant future. Part of the problem with this is that it's at very low energies, around about 100 milli electron volts, so one has to have a finely tuned beam to be able to map this out. But it's such a large effect that it should be readily observable. Finally, I'd like to finish up in the last 4 or 5 minutes with biological applications of positrons. So positrons as an imaging agent. Many of you may be aware of the use of positrons as an imaging diagnostic in positron emission tomography. There are also increasing uses of positrons as electrons are used in radiotherapy. There are new positherapy techniques being developed. And what happens in a PET scan is that the positron emitter, it's typically fluorine-18, which is a radioactive isotope, emits positrons, is latched to a molecule. The typical one is glucose to form this radiopharmaceutical called fluorodeoxyglucose. It's injected into the body as a liquid, and the carrier molecule, the glucose, finds sites of high metabolic activity, which can include a cancer. And so the glucose attaches itself to those areas of high metabolic activity, taking with it the positron emitter. The positrons are emitted at high energy. They thermalize in the body through scattering until finally they're at low enough energies that they form positronium, most likely, and annihilate. And it's the two annihilation gamma rays that are picked up in these PET scans. And they can use quite sophisticated software to analyze what the point of origin of the gamma rays were. And so this thermalization via scattering takes place over the order of hundreds of picoseconds, can be up to 15 to 20 millimeters depending on the nature of the tissue. And as I mentioned, the detection involves the coincident detection of these gamma rays. And this is an example of a PET scan where there's some tumours showing up here in this person as well as some of the bodily organs. So our interest here is, can we quantify positron interactions with biomolecules? Can we use the AM data that we can measure to help model positron transport, ultimately in soft condensed matter? And can we use this information ultimately to improve the efficacy of PET through and understanding better resolution, particularly understanding range of positrons, and collateral damage that's done by either positrons or secondary electrons that are produced. I'll have to go quick here because I'm down to my last few minutes. So the sorts of measurements we've been doing in this area on biomolecules are a range of things. We can measure total scattering, we can measure angular scattering, we can measure inelastic scattering. So these are for these are measurements for water, tetrahydrofuran, which is a sugar analog for the DNA chain, pyrimidine, a molecule which is a proformer of many of the DNA bases. And for uracil, there are measurements here for uracil, which is an RNA base. So we've done a whole range of these sorts of measurements. These are positronium formation cross-sections for a range of biological molecules, and again, they show this sort of typical structure. We take this information, and it might be either from experiment or from theory. A lot of it comes from theory. And then we put it into, with our colleagues, put it into Monte Carlo or Boltzmann type models to model the positron transport in various media. So the scheme of things is that we measure these cross-sections, we put them together in a cross-section set, we add things like an energy loss distribution function to that cross-section set. That all goes into the Monte Carlo code, and then we can extract things like tracks of charged particles in water or in whatever medium we feed into the Monte Carlo code. And I should point out that all of this stuff now is based on real data in many cases, either real data or reliable cross-sections. This is an example of one such track model. This is from Gustavo's group in Madrid. And it's the last few picoseconds of an 800 eV positron in water, at 1 atmosphere of water. And what happens here, so all of these, there's a chart here that goes from positronium formation in the red all the way down to elastic scattering in the blue. And what happens here is that the positron comes in, there's a whole range of collisions taking place, there are secondary electrons being produced. And at this point, there's an Auger collision where the positron loses most of its energy and then very shortly after that forms positronium and annihilates. So this is where the track ends for the positron. But the Auger electron goes off, ionizing, producing secondary electrons, and one of those secondary electrons actually causes a dissociation of the water molecule. So this is the sort of information that can tell us about damage that's taking place as a result of charged particle interactions in the medium. A similar type of track model has been pursued by Zoran Petrovic and his colleagues in Belgrade. And this is actually interesting because this is somewhat more interesting because it's in a mixture of molecules. So we're getting to the stage now where we've got enough information that we can have mixed varieties of molecules and look at positron tracks. So this is the start of the positron here, the little star, and this track are all the interactions that take place before positronium formation. But then all of the other blue points in here are secondary electrons that are produced. And there's a whole sea of secondary electrons. And the dark blue points are points where dissociation of the methane molecule is taking place. And that's, again, where there might be, one might suspect that there could be damage. I'm going to finish up here almost with something strange that we found in the trend for positronium measurements. One might typically think that the maxima here in these positronium cross-sections would largely scale with the number of electrons that you have in the system. And for the rare gases, we see that they increase, the positronium cross-section increases as we go to the heavier rare gases. But there's some really interesting anomalies here. One that's not so anomalous, for instance, is that neon, which has the same number of electrons as water, the cross-sections are about an order of magnitude different. And that's, we interpret, because of the dipole interaction in the water molecule. What's very strange, though, is that hydrogen, if I can find, I don't have hydrogen. That's interesting. I look like I've got the wrong. Anyway, I can tell you what it looks like. The hydrogen The hydrogen cross-section, positronium cross-section, looks almost exactly the same as water. And hydrogen's got 2 electrons, water's got 10, and it's polar, but the H2 cross-section is anomalously large. So there's a whole range of interesting features that are starting to come out of this type of information. So to conclude, I think the major advances in lepton scattering technology in theory, particularly theory, over the past 20 years. There's some really interesting challenges that remain for electron collisions. I think there's a lot to be done still with excited states and radicals. We've seen at this conference and at the associated satellite conference that DEA with biomolecules is a really important and flourishing area in electron physics at the moment, and I think that's going to continue. There are many challenges in positron physics. I mentioned positronium scattering. There's some really beautiful experiments that are done now at University College where they've indicated that when you scatter positronium from a rare gas or a molecule, it looks more like electrons scattering than the positron scattering. So the solid line here is this is in CO2, solid line here is the electron scattering cross-section for CO2, the dots are the positronium scattering cross-section, including a resonance, and the bottom curve here is the positron cross-section. So positronium wants to align itself and it look like an electron when it scatters from an atom or molecule. And of course there's these open questions around atomic bound states, resonances and dissymmetry. And with that I'll say that we're developing a reaction microscope for positrons at the ANU. That's underway at the moment. But there I'll finish and I will thank you very much for your attention and I'll invite you all to come and see us in a couple of years in Australia. Thank you very much.